please pause the video and try this problem. I hope you did try the problem, and now let's discuss it. You should regard this problem as a test of how well you've learned the material that we've covered so far in this video series. This problem is the first problem in this video series that deals with a vertical surface rather than with a horizontal surface or with an inclined plane. But as I said, this problem is still a good test of how well you've learned the material that we've already covered, because we should be able to deal with this vertical surface simply by adapting the concepts and techniques that we've already learned how to apply to horizontal surfaces or to inclined planes. First, we choose our problem-solving frameworks. The problem mentions concepts of mass. Here's a force. Here's friction, which is another force. Those concepts indicate that we should be using the Newton's second law problem-solving framework. The problem also mentions distance concepts and speed. Those concepts fit into a kinematics framework. So we're going to apply Newton's second law and general one-dimensional kinematics. We're applying general kinematics to indicate that we're not applying projectile motion. And it's one-dimensional kinematics because the object is moving in a straight line. If we choose these axes, we can see that the object in this problem will be moving vertically in the y component. So for this problem, we should say that the connecting link between kinematics and Newton's second law will be a sub y. Let's make a note of what the question is asking us for, the block's speed when it reaches the top of the wall. Speed is a kinematics concept. So I'm going to do some more work on the best way to represent this question later in the video when we start working with our kinematics framework. Now let's indicate the object's direction of motion. The problem says that Jessica is pushing the block up the wall. That wording implies that the object is moving up the wall. So we'll draw an upward velocity vector to indicate the object's direction of motion. Now let's identify the forces for our free body diagram. First, we identify the force of the object's weight. Next, we ask what is touching the block. The block is being touched by the wall, and a wall is the type of thing that we treat as a surface, which means that the wall will exert a normal force on the block. Anytime you identify a normal force, you should automatically check whether that surface is also exerting a frictional force. And we can see from the problem that this wall does exert friction on the block. So we're also going to identify a frictional force. The block is sliding up the wall. Since it's sliding, we know we should be applying kinetic friction rather than static friction for this problem. Is there anything else that's touching the block besides the wall? Yes, Jessica is touching the block. So we also have to identify the force being exerted by Jessica on the block. That force that's exerted by Jessica on the block was mentioned explicitly in the problem and was also represented explicitly in the sketch that we were provided. So we identify the force that's being exerted by Jessica on the block as another of the forces for our free body diagram. The problem does not tell us what symbol to use for that force, so I'm going to use the symbol F sub j. We use capital F for this force because lowercase f should be used specifically for frictional forces. And I'll use a subscript j because it's being exerted by Jessica. If you prefer, it would be perfectly fine to instead represent this force as F sub applied. Are there any other forces on the block? Well, is there anything else touching the block besides the wall and Jessica? No, nothing else is touching the block, so there are no other forces being exerted on the block. Now let's discuss the directions of the forces. We use these rules for the directions of the forces. As usual, the direction of the weight force is straight down. The direction of the normal force should be perpendicular to and away from the surface that is touching the object. So the direction of the normal force exerted by the surface of the wall on the block should point perpendicular to and away from the surface of the wall. That would be this direction to the left. So for this problem, the normal force points to the left. Now, the direction of the kinetic friction force should be parallel to the surface and opposite to the direction that the object is sliding. So the direction of the kinetic friction force exerted by the surface of the wall on the block should be parallel to the surface of the wall. Well, the wall is a vertical surface. So parallel to that surface would also be vertical. So the friction force for this problem must be vertical. The block is sliding up the wall, so to oppose that sliding, the kinetic friction force has to point down. So let me ask you a question. Did you correctly identify the direction of the normal force and the direction of the kinetic friction force for this problem? Remember, that's a good test of how well you've learned these rules that we've been discussing in the previous videos. If you got these directions correct, excellent. And if you got these directions incorrect, that means that you need to do more work on applying these rules. This is the first problem in this series in which we dealt with a horizontal normal force and a vertical frictional force, because this is the first problem in this series in which we've been dealing with a vertical surface. Remember, the normal force should be perpendicular to the surface, and the friction force should be parallel to the surface. Finally, of course, it should be straightforward to identify the direction of Jessica's pushing force, because that direction was described in the problem and also represented in the sketch that we were given. Next, let's work on the force table. We are given a value for the magnitude of Jessica's pushing force, 210 newtons. So we write that value here in the first row of the force table. We have special formulas for the magnitude of the weight force and the kinetic friction force. And we represent the magnitude of the overall normal force with a symbol. Before we break the forces into components, we need to choose and write down our axes. Now, the block is moving up. So let's choose a positive y-axis that's pointing up. And I'll choose a positive x-axis that points to the right. Now, the kinetic friction is anti-parallel to our y-axis. The normal force is anti-parallel to our x-axis, and the weight force is anti-parallel to the y-axis. So for all three of those forces, we can apply this rule to break all three of those forces into components. For example, the normal force is pointing in the negative x direction. So the x component of the normal force is negative, and the x component has the same magnitude as the overall normal force, and the y component is 0. In the previous videos in this series, the normal force has had a 0 x component and a non-zero y component. This is the first problem in the series where the normal force has a 0 y component and a non-zero x component. This is also the first problem that we've seen for which the non-zero component for the normal force has been negative. For another example, the kinetic friction force is pointing down, which is our negative y direction. So the y component of the friction is negative. The y component has the same magnitude as the overall friction, and the x component is 0. For the previous problems in this video series, the y component of the frictional force has been 0, and the x component has been non-zero. This is the first problem in this series where we've seen a frictional force that has a 0 x component and a non-zero y component. Now, Jessica's pushing force is neither parallel nor anti-parallel to either axis, so we will not use this rule to break Jessica's force into components. For Jessica's force, we need to use the SOHCAHTOA process. We need to draw a right triangle in order to break this pushing force into components. Do not draw the right triangle in your free body diagram. That will make this diagram too messy. Let's draw a separate diagram just for the purpose of breaking the pushing force into components. Remember that if you thought it was easy to break this force into components, you can skip our discussion of that process by using the table of contents and the progress bar. We draw the legs of the right triangle parallel to our axes. On this problem, we're using horizontal and vertical axes, so we have horizontal and vertical legs. Then the overall force represents the hypotenuse. The pushing force is directed up and to the right, and therefore the components are up and to the right. That allows us to determine that both components are positive. Use an asterisk to label the angle that you're focusing on in the right triangle. We're choosing to focus on this 32-degree angle that we have been given, rather than this angle. So here's where I put the asterisk. This side is labeled as the hypotenuse because it's across from the right angle. This leg is labeled as adjacent because it's adjacent to the 32-degree angle that we're focusing on. And this leg is labeled as opposite because it is opposite to the 32-degree angle that we're focusing on. Which leg is opposite and which leg is adjacent depends on the angle that you're focusing on. If we had chosen to focus on this angle, then we would have different labels for which leg is opposite and which leg is adjacent. That's why it's helpful to label the angle that you are focusing on with an asterisk. Now we can use our SOHCAHTOA equations. Our sketch now shows us that the length of the opposite side represents the magnitude of the x component, and the length of the adjacent side represents the magnitude of the y component, and the length of the hypotenuse represents the overall pushing force. Remember, the problem told us that the overall pushing force had a magnitude of 210 newtons. It's impossible to get this part of the SOHCAHTOA equations correct unless we have correctly labeled the opposite and adjacent sides in our right triangle. Now we can solve our equations for the magnitudes of the components. And then in a separate step, we have to add plus or minus signs to the components. The x component is pointing to the right, which is the positive x direction, and the y component is pointing up, which is the positive y direction. So both components get plus signs. Now, for the problem that we are working on in this video, we used sine to find the magnitude of the x component, and we used cosine for the y component. But compare that to the different pattern that we used for the first video in this series. Here's our work on breaking the tension force into components back from the first video in this series. In that problem, we used sine for the y component, and we used cosine for the x component. The moral is that you can't assume whether you're going to use sine or cosine for the x or the y component. You have to apply the SOHCAHTOA process to determine the correct approach for each individual problem. Notice that for the problem in this video, the y component was adjacent and the x component was opposite, whereas for the problem in video 1, the x component was adjacent and the y component was opposite. So we can see that a key to the SOHCAHTOA process is using an asterisk to label the angle that you're focusing on in the right triangle, and then carefully and correctly labeling the opposite and adjacent and hypotenuse sides in the right triangle. So let me ask you a question. Were you able to correctly break this pushing force into components for this problem? If so, excellent. If you were not able to correctly break the pushing force into components, though, that indicates that you need to do more work on applying this SOHCAHTOA process. You want to get to the point where it's boringly easy to correctly apply the SOHCAHTOA process to break forces into components. Now we can substitute our results for the components into the force table. Put a plus sign in front of each positive component. That will help you to notice the crucial negative signs that we need in front of our negative components. I believe this is the first problem in this video series where we were dealing with 4 forces. When you're dealing with a lot of forces, be extra careful to draw a large, clear, accurate free body diagram and draw a large, clear, accurate, organized force table. Now let's set up our Newton's second law equations. For this problem, the block is moving vertically. The block is moving in the y component. For this problem, the block has no motion horizontally. The block is motionless in the x component. So for this problem, a sub x is 0. In the previous problems in this video series, we dealt with objects that were motionless in the y component. So for the previous problems in this series, a sub y was 0. But for this problem, we're dealing with an object that is motionless in the x component. So for this problem, a sub x is 0. When you tried this problem on your own, did you get that right? Did you see that for this problem we have to substitute 0 for a sub x? Now let's shift gears and set up the kinematics framework for this problem. The problem tells us that the box begins from rest and then begins moving. That means that the block's speed increases. And since the speed is changing, we know that the velocity is changing. So we know that we will not apply constant velocity for this problem. The forces on the block are constant, so the net force is constant, so the block's acceleration is constant. Net force determines acceleration. For this problem, we will apply the kinematics of constant acceleration with changing velocity. The block is going to move from here up to here, and I'll draw this arrow on this line segment to indicate that this line segment represents the path of the block's motion. For a kinematics problem, we should attempt to build as much kinematics information as possible into our sketch. For example, the problem tells us that the block begins 0.6 meters above the floor. So we can label that the distance from here to here is 0.6 meters. The problem tells us that the wall is 1.8 meters high. So we can label that from here to here is 1.8 meters. Notice that whenever you label a distance in your sketch, you should carefully indicate where the distance begins and ends. Let's label the key points in time as t sub 0 when the block begins moving. Let's set t sub 0 equal to 0, and t sub 1 when the block reaches the top of the wall. The problem tells us that the block begins at rest. We can build that information into our sketch by saying that the velocity at time 0 equals 0. The object is moving vertically in the y component, so we're going to be applying kinematics to the y component. So I focus on writing down the value for the y component for this kinematics variable, v sub 0 y. We already noticed that the question was asking us for the block's speed at the top of the wall. And now, if possible, we'd like to represent that question with a symbol and build it into our sketch. Well, we know that speed represents the magnitude of the velocity. So we can use the symbol v, written without an arrow on top, to represent the magnitude of the velocity, which is the object's speed. And the question is asking us for v sub 1, the magnitude of the velocity at time 1 when the object reaches the top of the wall. Now, we want to think in terms of components. For this problem, the object is moving only in the y component. So the magnitude of the velocity at time 1 will be the same as the magnitude of the y component of the velocity at time 1, which we can represent with this symbol. And the object is moving upwards, which is our positive y direction. That means that this y component will be positive, and that means we don't really need these absolute value signs. So we've determined that we can represent what the question is asking us for with the symbol v sub 1y. And now we can build that into the sketch. When possible, represent what the question is asking you for with a symbol, and when possible, build the question into your sketch. Let's label t sub 0 and t sub 1 as our initial and final points. Those are the points that we are going to substitute into our kinematics equation. Now we can work on our kinematics setup, which consists simply of a list of the 5 general kinematics variables. Think in terms of components. On this problem, the object is moving in the y component, so we're going to apply kinematics to the y component. So we write down the 5 kinematics variables for the y component. We've determined that figuring out v final y will tell us the answer to this question. So let's write a question mark above the variable v final y to indicate that that's what we need to answer the question. Now we try to substitute specific numbers or symbols for each of those variables. For delta t, we don't have anything more specific to use than delta t. Let's come back to delta y in a few moments. The initial y we already indicated in our sketch is 0. That's because the problem tells us that the block begins at rest. For v final y, we can use the slightly more specific symbol v sub 1y, the y component of the velocity at time 1. For a sub y, we don't have anything more specific to use than the symbol a sub y. Remember that we were expecting that for this problem, a sub y will be our connecting link between kinematics and Newton's second law. So we can see now that it looks like we're going to use the Newton's second law y equation to determine a sub y. Then hopefully we'll be able to substitute that into our kinematics setup and use that value for a sub y to determine v final y. Now let's determine delta y. Although, of course, if you thought it was easy to determine delta y, you can skip this discussion using the table of contents. Well, what does delta y stand for? Delta y stands for the y component of the displacement between the initial point and the final point. The block is being displaced from here to here. So this colored arrow represents the block's displacement from here to here. The block is moving only in the y component. So this colored arrow also represents the y component of the displacement. Build that into the sketch. So now I've built into the sketch that delta y represents the displacement from here to here. Now we can determine the numerical value for delta y. First, determine the plus or minus sign. The object is being displaced upwards. Upwards is our positive direction, so delta y is positive. We include a plus sign in front of a positive component because that will help us to notice when a component is negative. Now the magnitude of delta y represents the distance from here to here, and because we've built a lot of distance information into our sketch, it should be apparent that the distance from here to here will be 1.8 meters minus 0.6 meters. From this distance and this distance, we can determine that the distance that the object is being displaced is 1.8 meters minus 0.6 meters, which is 1.2 meters. Now we can build our value for delta y into our setup. When you worked on this problem, were you able to determine the value for delta y correctly? If not, then you probably need to work more on building available information into your sketch. The problem did not build the 1.8 meters and 0.6 meters numbers into the sketch for us. It just gave that information in the text. It was our job to take that information from the text and build it into the sketch. Once we build those distances into the sketch, it should be apparent how to determine delta y. Also notice how labeling the initial and final points made it easier for us to correctly label the displacement of the block in our sketch. When you build distance information into your sketch, always carefully label where each distance begins and ends. Do you see how this would be a bad version of the sketch? This is a poor version because although I've put these numbers in the sketch, I haven't put in any indications of where each distance begins and ends. And without those indications, we're much less likely to interpret the sketch correctly. So here again is the superior way to build distance information into the sketch. Make a large sketch so that there is sufficient room to clearly include all the labels that you need to in your sketch. We've completed our setups now for both the kinematics and Newton's second law frameworks. Which of these three columns should we work with first? Well, we're ready to choose a kinematics equation when we know values for 3 kinematics variables. So far, we only know values for 2 kinematics variables, so we're not ready yet to choose a kinematics equation. Newton's second law y equation has 2 unknowns, so we're not ready yet to work with this equation. The Newton's second law x equation has only 1 unknown, n. So now would be a good time to solve the Newton's second law x equation for n. In order to solve this equation for n, we need to separate these 2 terms. I think that most students would probably begin that process by moving this term to the right of the equation, and that would be perfectly fine. But it's a little bit more efficient to move this term to the right side of the equation by adding n to both sides. That's a little bit more efficient because that also allows us to get rid of this negative sign at the same time. Our result is that n equals 111.3 newtons. Now, we substitute our value for n into the Newton's second law y equation. Once we've done that, now the Newton's second law y equation has only 1 unknown, a sub y, and we can now use algebra to solve this equation for a sub y. And we get the result that a sub y is positive 2.26 meters per second squared. For each of the previous problems in this video series, we began by solving the Newton's second law y equation for n, and then we substituted that into the Newton's second law x equation. In contrast, for this problem that we're working on in this video, we began by solving the Newton's second law x equation for n, and then we substituted that into the Newton's second law y equation. It was clear that for this problem, we needed to begin by working with the Newton's second law x equation rather than with the Newton's second law y equation, because originally the Newton's second law y equation had 2 unknowns, whereas the Newton's second law x equation began with only 1 unknown. Now we take our result for a sub y and substitute it into our kinematics setup. Remember, we were expecting from the beginning to use a sub y as our connecting link between Newton's second law and kinematics. Now we know values for 3 kinematics variables, delta y, v initial y, and a sub y. Since we know values now for 3 kinematics variables, we're ready now to choose a kinematics equation. We want an equation that includes delta y, v initial y, and a sub y, because those are the variables we know, and we want an equation that includes v final y, because that's what we need to figure out. So the one variable that we do not care about is delta t. So let's pick a kinematics equation that's missing delta t. On the kinematics handout, we used this box to find the kinematics equations for constant acceleration with changing velocity. And the equation that is missing delta t is this equation. Notice that for this problem, we're applying kinematics to the y component. So we pick a kinematics equation that refers to the y component. The equation is v final y squared equals v initial y squared plus 2a sub y delta y. Again, the equation is referring specifically to the y component. Think in terms of components. For v final y, we substitute v sub 1y. For v initial y, we substitute 0. For a sub y, we substitute 2.26 meters per second squared. For delta y, we substitute 1.2 meters. That's the number that we figured out in our sketch by subtracting 1.8 minus 0.6 meters. At this point in our work, we have to take a square root. Any positive number has both a positive and a negative square root. So should we take the positive or the negative square root at this point? Well, the object is moving upwards, so the velocity points upwards. Upwards is our positive y direction, so the y component of the velocity should be positive. So we take the positive square root. Our result is that v sub 1y equals positive 2.33 meters per second. When you get a result, include units with your result. All the numbers that we substituted into our equations were in SI units, so we can trust that our result will come out in SI units. The SI units for velocity are meters per second. Now we can answer the question. The question was asking us for the block's speed at the top of the wall. Speed is the magnitude of velocity. We found that the magnitude of the velocity at the top of the wall is 2.33 meters per second. I'll round that off to 2.3 meters per second for our answer. This object is only moving in the y component, vertically. So for this problem, the vertical speed also represents the overall speed. Make sure that you've answered the correct question and that you've answered all parts of the question. For example, the question could have asked how long it takes to reach the top of the wall. So make sure you're answering the right question. Make sure that your answer includes units. Let's check if our results make sense. It makes sense that this result is positive because this symbol stands for a magnitude, and magnitudes can never be negative. The magnitude of the normal force came out to equal the magnitude of the x component of the pushing force, 111.3 newtons. Why does that make sense? Well, this rightward pushing force is trying to begin the block moving to the right through the surface of the wall. To prevent the object from being pushed through the wall, the normal force is going to have to cancel the x component of the pushing force. So it does make sense that the normal force has to equal the x component of the pushing force in magnitude. In this version of the free body diagram, I tried to draw this arrow the same length as this arrow to show that the normal force needs to cancel the x component of the pushing force. Notice that for all the previous problems in this video series, the normal force was related in some way to the weight force. But for this problem, there was no relationship between the normal force and the weight force. Instead, for this problem, the normal force was related to Jessica's pushing force. The moral is, don't make assumptions about the normal force. Just let your Newton's second law equations figure out the normal force for you. Now let's check if our result for a sub y makes sense. Does it make sense that a sub y is positive? Well, our positive y direction is up. So this result indicates that the acceleration points up. As I've drawn here, since a sub x is 0, the overall acceleration points in the same direction as the y component. Does it make sense that the acceleration points up? Well, we know that the block begins at rest and then begins moving upwards. In order for the block to begin at rest and then begin moving upwards, the acceleration must point up. So yes, it does make sense that the acceleration points up. It makes sense that a sub y is positive. Does the magnitude of this result make sense? Well, this magnitude is inside the typical range, between 0.1 and 10 meters per second squared for acceleration. So in that sense, this result does seem reasonable. Does a result for v sub 1y make sense? Does it seem reasonable that by the time it reaches the top of the wall, the block will be moving at about 2 meters per second? Well, most people are not used to using meters per second in our everyday lives. If you live in the US, you're much more used to using miles per hour in your everyday life. So it's useful in that case to know that 1 meter per second is very roughly 2 miles per hour. So the number of miles per hour is roughly twice the number of meters per second. So if our result is about 2 meters per second, then that would be roughly 4 miles per hour. Does it seem reasonable that somebody could push a block and make it start moving at around 4 miles per hour? Yeah, I think so. 4 miles per hour does seem like a reasonable speed that somebody could attain by pushing on an object. By the way, if you live outside of the US, you probably don't use miles per hour in everyday life. Instead, you probably use kilometers per hour in everyday life, and in that case, it would be useful to know that 1 meter per second is very roughly 4 kilometers per hour. So how well did you do on this problem? As I said at the beginning of this video, this problem is a good test of how well you've been learning the material that we've been covering, because while the situation in this problem is somewhat different from the situation in the previous videos, because here we're dealing with a vertical surface rather than a horizontal surface or an inclined plane, this problem is still a good test because we should have been able to get this problem right simply by adapting the concepts and techniques that we've been learning in the previous videos. So, given that in this problem we were dealing with a vertical surface, how did that affect our solution? It affected the directions of the normal force and the kinetic friction force. Remember that the normal force should be perpendicular to the surface, and the kinetic friction force should be parallel to the surface. It affected the pattern of our components. For example, I believe that this is the first problem we've worked on where we ended up with a negative component for the normal force. It affected how we dealt with a sub x and a sub y. In this problem, the object was motionless in the x component, so we substituted 0 for the x component of the acceleration. Since the object is moving vertically in the y component, we applied kinematics to the y component. On previous problems, we began by solving the Newton's second law y equation for n and substituted into the x equation. But for this problem, we began by solving the Newton's second law x equation for n and substituted into the Newton's second law y equation. Another issue that arose on this problem was correctly determining delta y. If that was difficult for you, as I said earlier, the key is making a clear sketch and building as much of the distance information as possible, as clearly as possible, into your sketch. Another issue on this problem was correctly breaking the pushing force into components. To do that correctly, you have to correctly identify which component is adjacent and which component is opposite in your component's right triangle. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.